SwayamPrabha. Digital India. Educated India.
Today we will discuss oxidation and hot corrosion phenomena. So, today's discussion is oxidation and hot corrosion, and this oxidation means mainly reaction of metal with oxygen at high temperature. So, let us first get into oxidation. The first scientific studies on oxidation is done, it is basically from a ratio people used to determine whether the material has very good oxidation resistance or not. That ratio is called filling Bedworth ratio. Filling Bedworth ratio, it is basically a sort of qualitative approach in order to understand the oxidation resistance of a particular metal or alloy. This ratio is basically termed as R, and this is the ratio between the molar volume of metal oxide and molar volume of metal. But here one thing is to be taken care of, that is this W, small w means the weight of metal which is getting oxidized, and this capital W is the weight of oxide. So, small w is molecular, is basically the molecular weight of metal which is getting oxidized, and small d is specific density of metal. Similarly, capital W is the molecular weight of oxide, and that time we have to be careful that if 1 mole, we have to always consider 1 mole of metal which is getting oxidized. Now, depending on the situation, whether 1 mole is giving half a mole oxide or 1 mole is giving 1 mole oxide, this molecular weight of oxide is to be divided by a particular factor. Actually, it says that when 1 mole of oxide is going, 1 mole of metal is getting oxidized, what would be the volume of oxide that would be forming? And this capital D is specific density of oxide. Now, in order to understand how the factor would be decided, there should be a factor which would be coming in this particular ratio while we consider oxidation of 1 mole of metal. Now, for example, if the reaction is of this sort, that means this is 3 by 2. If the reaction is of this sort, that means 1 mole of metal is getting oxidized and forming M2O3, and that is nothing but the half a mole of oxide that is forming. Now, in that case, this half factor would come here, it is to be multiplied with this particular ratio will be multiplied by half, because 1 mole of oxide is giving half a mole of 1 mole of metal is giving half a mole of oxide. Now, if the reaction is of this nature, that time 1 mole is giving 1 mole of oxide, there the multiplication factor would be 1. So, in order to understand it better, let us calculate some value of R for few oxides. Let us consider Al2O3. Al2O3, the reaction nature would be of this kind. So, that means here aluminum plus 3 by 2 O2, it would form half Al2O3. Now, that case, if we know the value of capital W of Al2O3 from the atomic weight of all the elements, and as well as how many atoms are there in the particular molecule, 1 mole of molecule, that time 1 mole of oxide, we can determine the W becomes 101.96 gram, and we can also determine the density of this oxide. Density of the oxide is 3.89 gram per cc. Now, again we can determine what is the small w. Small w is 26.98 gram and small d is 2.7 gram per centimeter cube. Now, if we put all the values and with the factor half, so this R becomes 101.96 divided by 2 into 3.89 and then 26.98 divided by 2.7, and this ratio becomes 1.308 and the reported value is around 1.28. So, it is almost close to that. So, this we can make it 1.3. So, this value and this value, the reported value as well as the calculated value is coming same. And then let us find out one more oxide, let us say chromium oxide. Chromium plus, again the reaction would be of this nature, same like Al2O3, the calculation mode would be same, and here also we need to put the factor 2, half is to be multiplied with this particular ratio in order to get R. So, here also we can find out the W, capital W of oxide is 152 gram, capital D is 5.210 gram centimeter cube, and this density can also be found out by simply considering the density of chromium and oxygen and then having the atomic ratio, the way they are mixed, we can also find out this value would be close to this. So, then small w would be 52 and small d is 7.14, that time this R would be half into 152 divided by 5.210, 52 divided by 7.14, this would become 2.0029, and the reported value, reported R, is 1.99, which is close to 2. So, that means these are the examples, two examples with respect to the first equation, and let us also find out one R value with respect to the second type of equation, where let us find out here, let us find out for FeO, Fe plus half O2 FeO. So, W FeO is 55.85 plus 16. 16 is the atomic weight of oxygen, 55.58 is the atomic weight of iron, divided by 5.745, which is the density of FeO, and then this R equal to this. This is basically the W of FeO, and this is the density of FeO, and then for FeO is basically the weight of iron. 1 mole of iron is 55.85, and the iron density is 7.86, and this would become 1.76, and the reported value is 1.77. So, it is coming close. Now, what it means that when 1 mole of atom, 1 mole of metal is going to getting oxidized and forming metal oxide, if the molar volume of metal oxide is more, then it is going to cover up the entire surface. And now, if it is less, it is not going to cover up the entire surface. So, we can have some exposed area of the metal where oxidation can take place, but if it can cover up, the entire surface, then we can have a good resistance which is expected, provided that the metal oxide is not evaporating type. For example, in case of vanadium, the V2O5, that is the oxide that forms in case of vanadium, that V2O5 evaporates. So, when it evaporates, that time it cannot stay with the surface of the metal. So, it cannot give any oxidation resistance. So, the to be protective, for the oxide to be protective, that means if we have oxide layer. So, oxygen has to diffuse through the oxide layer, or metal ion has to diffuse out through the metal oxide. Later, this has been understood that there would be diffusion of metal ion or oxygen ion through the metal oxide. That is what the oxidation goes on. So, if you have oxide, that means it is forming. Actually, previously there was one understanding that it provides a sort of protective layer, where you can cut where basically the contact between oxide and metal is disrupted. So, or disturbed. So, that is where the resistance comes. Now, in order to be protective, few things are to be remembered. Oxide to become protective, few things. One is when you have oxide, that time the thermal expansion coefficient of that oxide and metal should be similar. If they are not similar, then there would be stress generation in the oxide, and oxides are generally brittle in nature. They will crack and expose the metal surface to the oxygen gas. Now, second is they should be non-evaporative. Evaporation should not happen. So, for example, V2O5, it basically evaporates. So, it cannot give any protection. Now, since the reaction, most of the oxidation reactions or oxide growth is happening at high temperature. Now, if the metal object is under tension or is under stress, that time there could be possibility of plastic deformation of that oxide. Now, if that oxide is brittle in nature, the oxide can break. So, but if the oxide can possess sort of plastic deformation ability, it is always good for the oxide to be protective. So, plastic deformation ability of oxide. Now, again this has been understood later that there would be always diffusion of metal ion as well as oxygen ion through the metal oxide layer. So, if we can make the oxide to be very stable as well as to be impervious, or if they have sort of low diffusion coefficient, of the metal ion species or the oxygen ion species through the oxide, then the oxide is generally thought of having a very good protection ability. So, we see that these are the common features that oxide should possess to have a very good protection ability of that oxide against further oxidation of that metal. So, this is roughly about this peeling Bedworth ratio. This is a very primitive understanding about the oxidation resistance of metals or alloys. Now, later on more detailed explanation about this oxidation process, its mechanism, those have been studied and understood. Let us get into some of the recent understanding of oxidation of metals and alloys. Now, whenever oxidation takes place, that time there would be some sequence of events. Before getting into the thermodynamic as well as kinetic understanding of oxidation, let us see what will be the sequence of events that might occur during oxidation of a particular metal object. The sequence of events. During oxidation. Now, the first thing which can occur, let us say the metal surface is exposed to the oxygen environment. Now, the first thing that can happen, so you have oxygen gas, G means gas. So, they come in contact with metal surface and they get decomposed, and after decomposition, after they get decomposed, so they get absorbed on the metal surface. So, adsorption of oxygen to the metal surface. So, this is my metal surface, and on which oxygen are basically oxygen atoms are getting absorbed onto the metal surface. This is the first event that can happen. Now, the second event would be now this is happening at temperature T, and this is also happening at some particular partial pressure of oxygen. Now, at the temperature T, depending upon the thermodynamic ability of that metal to get oxidized and to form oxides, because of the reaction between oxygen and metal, if that is satisfied, then oxide can form on the metal surface. So, this is the after adsorption of oxygen, once the thermodynamic condition is reached, which will enable that metal to react with the oxygen and form oxide on the metal surface. So, oxides are forming. Let us say the oxide nature is MO or MO2. Let us say the oxide nature is MO2. Let us consider the oxide nature is MO. So, the metal oxide is forming, and now this metal oxide, they are forming like islands on the metal surface, and they would try to grow in the lateral direction. So, that means the second event would be at temperature T, if the thermodynamic criteria is met for the formation of metal oxide, then metal oxide would form, and then this metal oxide would try to grow. So, the thermodynamic criteria is reached, of course, the kinetic is to be satisfied in order to form this metal oxide, but if you have enough supply of oxygen as well as the partial pressure of oxygen for the formation of oxide is maintained, and if it is higher than the partial pressure of oxygen that is needed, oxide formation is possible. So, thermodynamic criteria meeting thermodynamic criteria. So, this is the stage 2, and then this is first step 1 in the case 2 for the sequence 2, case 1, case 2 would be oxide formation on the metal surface, and then third one would be these oxide would grow laterally in order to cover up the surface. So, lateral growth, and the fourth event would be, so oxygen are still adsorbed on the metal surface. So, the oxygen are still adsorbed on the metal surface, and since it is happening at high temperature and depending on the diffusion ability of that oxygen atom, adsorbed oxygen atom, that oxygen can also diffuse into the metal. So, oxygen diffusion can also take place. So, oxygen diffusion is taking place. So, actually the oxygen is getting dissolved in the metal. So, we can determine what would be the dissolved amount of oxygen in the metal from the phase diagram of that particular metal oxygen phase diagram, and from that we can determine what could be the percentage of dissolved oxygen that can stay in the metal without forming any oxide. So, this will be in the lattice. So, these are dissolved oxygen. So, fourth stage is basically dissolution of oxygen. dissolution of oxygen. So, this is the second stage of, or the second sequence of, second set of events that are happening in the second stage. Now, in the third stage, there would be, see the third stage, this oxide is growing this way laterally. Now, once the metal surface is covered up, so let us say the metal surface is covered up, this is the metal surface. So, this is the metal surface. Once the metal surface is covered up by the oxide, let us say this is my oxide layer that has formed on the metal surface. This oxide layer would try to grow in this direction. So, this is my metal surface and this is MO oxide layer. So, after it covers up the entire surface laterally, then they would try to grow in the perpendicular direction. So, the thickness of the metal oxide would increase. Now, once we have metal oxide, how would they grow? So, that growth process would be decided by the diffusion of metal ion as well as oxygen ion and the conduction of electron through this oxide layer. So, there could be oxygen, this side we have oxygen. So, oxygen can come in as in the form of oxygen ion, and they can come to this surface and react with the metal ion, or the metal ion can also diffuse out and then it can come to this surface and then again react with oxygen ion, then form metal oxide. And if this event is happening, that time electron can go there. So, now from this picture we can also have some sort of correlation between oxidation and aqueous corrosion. Now, at this point we see that oxygen is diffusing in, or metal ion can go out or diffuse out through this metal oxide layer, and there could be electron transfer from this surface to this surface. This can give you a sort of this can be correlated with the aqueous corrosion also. Now, if you see the aqueous corrosion, so we need 4 things for the aqueous corrosion to happen. One is cathode, second is anode. So, cathode surface cathodic reaction would happen, anode surface anodic reaction would happen. Then third case we have a solution which is nothing but electrolyte. Then we have conductor, which actually transfers electron. So, these are the 4 components for aqueous corrosion. And if we see that, for example, if we see that this is my zinc rod, and if it is in HCl medium, we see that zinc corrosion can take place. So, what happens? Some places, there are places where zinc will go out in the form of zinc ion, and how the zinc ion would be forming, then zinc actually would 2 electrons will be taken out from zinc, and then zinc ion would form, and this zinc ion, this 2 electron would go here near the place, around this place. So, there hydrogen ion would take care of this electron and then form hydrogen. So, this is my anodic reaction, this is cathodic, and then these electrons are basically transmitting through the conductor, which is the zinc rod, and electrolyte, which is the HCl solution, which is acting as electrolyte. Through that the ionic conduction is taking place. Now, here if we come to this place, let us say the general reaction MO, M plus plus O minus minus, if these two things react, then we can have M O. So, that time we have MO formation, and now first M plus plus, in order to form M plus plus we can have this reaction. It can, two electrons can be taken out from the metal atom, and then it will form M plus plus, and these two electrons can go to the oxygen. So, oxygen can take this two electron and form oxygen ion. Now, this is anodic reaction, and this is reduction or cathodic reaction. So, this and this will react. Now, react and then form MO. Now, this process can happen on this surface, because here we have metal surface. So, this reaction is happening at this surface, and the anodic reaction happening at this surface. So, this is my anode, this is my anode. Now, once we have two electrons which are excess in the metal, these two electrons can transmit through this oxide layer, and it can come here, it can come here, these two electrons, and then oxygen, adsorbed oxygen is already there. See, the adsorbed oxygen can take care of these two electron, can take these two electron, and then this reduction process can happen, can occur on this surface or interface. So, this interface is basically nothing but cathode. Since the cathodic reaction, wherever the cathodic reaction occurs, that surface is considered to be cathode. So, this is my cathode. So, that means if you compare this process and this process, so we have one anode and one cathode. Here also this is my anode, this is my cathode. So, two electrodes are done. This is my gas, this is my metal oxide. So, gas oxide interface is acting as cathode, and oxide metal interface is acting as anode. So, two electrodes are done. So, these two electrodes are done. So, conductor, this oxide itself is acting as conductor of electrons. So, the electron is this oxide is conducting electrons, which takes the electron from this surface to this surface. So, this is also done, this is done, this is done, and this is also acting as electrolyte, where we have, in this case, this process if you consider. So, here we have, if this process is happening on this surface, so on this surface we have oxygen ion, and then metal ion can go through this oxide layer, and whenever, and that means this is acting as a solution, just like in aqueous corrosion, where the ion movement is possible. So, this ion movement is taking place through this oxide. So, this oxide is also acting as electrolyte. So, all the four steps are there. So, this is acting as electrolyte as well as conductor. So, if metal ion goes from this end to this end, so metal ion will react with oxygen, and the oxide growth would take place on this surface, and if oxygen ion, there could be possibility of oxygen ion which can diffuse in and the metal ion will stay here. So, oxidation, that time oxidation would happen on this surface. So, this process is when oxygen ion diffusion in, oxygen diffuses in, and this is the case where metal ion diffuses out. So, this is the overall similarity between the oxidation process and aqueous corrosion, almost similar, because all the 4 components are also there in the case of oxidation. So, we see that there are resemblance between oxidation process and aqueous corrosion. Now, we were discussing the stage 3, where we see that oxide film is forming and that oxide film is growing gradually, and then we have oxygen and metal ion diffusion and the conduction of electron. Those events are also happening. Now, at the same time, there would be continuing dissolution process. Oxygen still would dissolve into the metal. Now, this process would go on, and finally, in the stage 4, we can have a defect formation in the oxide layer, because the continuous growth of, due to the continuous growth of oxide, and due to this diffusion process. Now, the stage 4, we can have defect generation. This is metal surface, oxygen diffusion is still taking place with the continuation of oxidation. Now, this metal oxide, now there could be cavity formation. This is my oxide layer, this is my oxide layer. So, this is one cavity. So, this is one cavity. This is one cavity that can form, and here if we can there could be a development of small crack like this. So, there could be development of small crack like this. So, oxygen can, the gaseous oxygen can go in through this cavity. There could be formation of pores in the oxide layer. Let us say this is my pore, this is my pore, this is cavity, these are pore. Even we can have micro cracks. This is micro crack formation, and of course, the other events, the previous events are also taking place continuously. Now, this is the stage 4, and then this is basically the defect generation, defect formation, and in the stage 5, this oxide layer, this is metal oxide. There could be a formation of macro crack like this. This is the formation of macro crack. This is my oxide layer. And this is my metal surface. This is my metal surface. So, oxide layer, and these are the macro cracks as well as cavity. Of course, there would be porous, there could be pore formation, more pore formation. So, like this the events are going on, as well as the oxide layer is also going on. Oxide layer is also, the thickness of the oxide layer is also increasing, and as well as the oxygen diffusion is also taking place. So, dissolution of oxygen is also taking place. Now, at this stage there could be other events, for example, even in the beginning, from the beginning of the process, there could be evaporation of oxide, or there could be possibility of embrittlement of the metal. Embrittlement of metal due to oxidation, and this oxidation could be internal oxidation, now this oxygen which is diffusing in, and that oxygen sometime the diffusion would be so fast, maybe if the oxygen is diffusing in through the grain boundaries, which are generally the open space region. So, that case the internal oxidation can also take place, and then that might lead to embrittlement effect of the metal. So, these are basically the series of events which are forming, which are happening, which are taking place sequentially. Now, this is when a metal, these are basically the steps or events which can happen during the metal oxidation. Now, let us see one reaction, what are the reactions that are possible. One reaction we have seen that the metal is basically reacting with oxygen. This is forming metal oxide, or this is half, or there could be this oxidation can be possible due to the presence of H2O, the vapor phase, as well as the presence of CO2. So, metal which can also get oxidized in the presence of water vapor. So, this is MO plus H2. If we would like to have a general balance, then we can put it like this: XM Y H2O, and then we can have MXY and then YH2. So, then the general balance is done. Then also we can also have oxidation of metal with due to the presence of CO2. Again, this is my general balance. So, M X O Y plus Y CO. So, these many reactions that could be possible during oxidation, either due to the presence of oxygen gas, or due to the presence of water vapor, or CO2. So, these are the common reactions which are encountered during oxidation of metal. Now, let us discuss the thermodynamic understanding of oxidation. So, thermodynamics. Whenever we talk about thermodynamics of any event, we basically consider the possibility of that process or event. Now, if let us say any process del G, which is the free energy change at constant pressure and time, if it is negative less than 0, we can say that the process is possible. So, possible reaction or event or process. Now, this particular concept would be considered while considering the thermodynamics of oxidation. Now, whenever we have a particular reaction, let us say M plus O2, it is forming MO. So, that means we can balance it like this. So, now in this process, this is let us say the solid phase, this is gas, this is let us say the solid again, the oxide which is forming, that is solid. Now, this process is happening at a particular temperature T, and let us say it is also happening when the atmospheric pressure is 1. Now, that time we can determine the free energy change for this oxidation process, and the free energy change for this oxidation process we can determine from the reaction isotherm. We have already talked about this reaction isotherm, which says that this is equal to minus RT ln K. So, this is my overall reaction isotherm, and this process, this K is the equilibrium constant in the non-standard condition. Now, this reaction, if it is not at equilibrium at that temperature T, then the free energy criteria can be written in this way. Now, if it reaches equilibrium, then we can also see the expression for K, which is basically MO2, or let me write it in the form of activity and partial pressure of oxygen. So, activity of MO and activity of M and partial pressure of oxygen. Now, if we put it here, then it would become del G 0, and if we consider these two phases, the pure metal is getting oxidized and forming the pure oxide, and that time, since they are pure, we can consider that their activity to be 1. So, then K would be equal to 1 by PO2. So, we can replace this K RT ln K and then we can say that this is 1 by PO2. I think I made a mistake here, it should be plus the reaction isotherm. So, this is if we replace the non-standard K with this equilibrium constant with partial pressure of oxygen, then the free energy change for this forward process is becoming del G 0 minus RT ln PO2. Now, if the process reaches this reaction reaches equilibrium, then this goes to 0 when at equilibrium. So, that time my del G 0 is coming out to be RT ln PO2. So, for oxidation, and this is nothing but the standard free energy change for oxide formation, and when the pressure is 1 atmosphere. So, this free energy change, which is the standard free energy change at temperature T, since the temperature is T here, and when the pressure is 1 atmosphere. That is the definition of standard condition, that the pressure will always be 1 atmosphere. And then once we know this, this will give you the idea whether oxide formation would be possible or not. Now, for the oxide formation, we should see that whether this condition is met or not. Now, let us say the oxygen partial pressure, which is the equilibrium partial pressure, let us say equilibrium partial pressure, which is determined from this equation. Once we get the value of del G 0 at temperature T, the equilibrium partial pressure at a particular temperature T, if it is less than the actual partial pressure that the metal is exposed to, PO2 actual, then what would happen? Let us see whether we have this condition or not. Now, if we see that, now we have to start with this equation del G, this equation, from this equation we have to start, and when we start from this equation, we can easily determine whether the oxidation is possible or not from the initial condition what we have, what has been written on this side. Now, if del G is considered, del G 0 plus RT ln PO2, and this would be the actual, and this case we can replace it with RT ln PO2 equilibrium. So, the equation is becoming RT ln PO2 equilibrium plus RT ln PO2 actual. Now, if this is more than this value, so what would happen? So, this would become positive. So, if the equilibrium partial pressure of oxygen at particular temperature T is less than the actual oxygen partial pressure that is existing on the metal surface, then we can determine what would be the free energy change. Now, if we consider this equation minus RT ln PO2, this is actual, and this part we can replace it with RT ln PO2 equilibrium. Now, since PO2 actual is greater than PO2 equilibrium, so this part always would be more than this part. So, this is then RT ln PO2 actual would be greater than RT ln PO2 equilibrium. So, then this term would be negative, so or less than 0. That means, this condition is met. So, the reaction is possible. So, oxidation is possible. So, oxidation is possible. Now, similarly, if we see that this is greater than this or this is greater than this, that time the things will reverse. So, this would be positive greater than 0 and then oxidation, second stage oxidation is not possible. So, depending on the oxygen partial pressure and its effect on the total free energy change, this del G, whether it is negative or positive, that would decide whether the metal would oxidize or not oxidize at that particular temperature with the existing condition of partial pressure of oxygen.